Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series. And this time, the topic is typical interview questions on protection schemes for persistence assets. My god name is John Kweko Amu-Otu, and I've been a professional electrical engineer for the past 31 years. I'm based in the United States of America. Now, let's go through the outline of my presentation. First item on the presentations slide is basically talk about the protection schemes for generator protection. Then we move on to protection schemes for power transformer and also protection schemes for motor. Then the last part of the list is parameters that you need to perform motor protection studies. Next slide. Okay, so this is a typical question that you should expect on generator protection and how you should answer it. Actually, this is meant for discipline engineers, maintenance engineers, project engineers, and technicians, maintenance technicians, and operators that have basic knowledge about protection systems. So this one is just a refresher for you, so that it gets you prepared for whatever interview that you have coming up. You know. The whole thing is, if you don't have any basic knowledge of protection systems on power system assets, then this will be very difficult for you to basically, grasp this information. So that is why it is a requirement, basic requirement for you to at least have some knowledge of protection schemes. So this one becomes like a refresher, or let's say any add-on that you need to add on to what you already know. Okay, so now let's talk about generator protection. So this is how you answer it. Okay, so for generator protection, you will say that generator protection is classified into the electrical protection elements, and abnormal operating condition. Now let's talk about abnormal operating conditions. Okay, so the first one is over frequency, right? Okay, so over frequency, you will say that okay, the ANSI designation for over frequency is 81O, right? Okay, so what it is the generator turbine generator manufacturer provides the protected relay engineer charts, right? That says that this is the allowable permissible frequency over frequency that you can operate based on a time duration. So this is what the protected relay engineer utilizes to set this over frequency. So let's say if you have a nominal frequency of operation of the generator as 60 hertz, right? Okay, so the turbine manufacturer will say that okay, I will allow you to go operate the generator, the turbine generator, at an over frequency up to 62 hertz, right? In between 60 to 62 hertz is going to be graded, right? Okay, so let's say above 60 hertz to 61 hertz, there's a time duration that will allow you to operate the turbine generator. Then above 61 hertz to 61.5, I will allow you a time duration. Then 61.5 hertz to 62 hertz, I will allow you a time duration to operate. Then above 62 hertz, that is when I want you to take the generator offline. So that's how we set this over frequency element. Likewise, for the under frequency element, the turbine generator manufacturer will provide you similar charts that will basically spell out the allowable, permissible under frequency operation that you are supposed to have. Okay, so let's say the allowable set point for the frequency element is 58 hertz. If you have a generator that is operating at a nominal frequency of 60 hertz, right? Okay, So this is the set point that basically the turbine generator will tell you that, okay, you need to trip the generator, because what is going to happen if you're operating below this, then basically your turbine blades are going to overheat and can cause a permanent damage to your turbine generator shaft. Okay, so in between 58 hertz and 60 hertz, right, that will also be graded, right? So from 60 hertz to, let's say, 59.5 hertz, there's going to be an allowable permissible duration in seconds that the turbine will be allowed to operate. Then from 59.5 hertz to, let's say, 58 hertz, the turbine manufacturer will specify the allowable time that you are supposed to operate this turbine generator. So that is what the under frequency element means. Okay, so now let's talk about loss of excitation, right? Okay, so let me explain that. Okay, so you have a turbine, then you have a generator, right? Okay. You have a shaft, then you have a generator shaft, right? Okay. Then in between that is a coupling shaft. Okay. So for the generator, it has a rotor, right? This is the rotor, right? Wound, and it has a winding that is wound on a shaft, right? Then it has a stator, right? Okay, so the winding on the rotor is fed with a DC voltage. And yes, of course, DC current from an excitation system, right? That is basically controlled by a voltage regulator, right? Okay, so what this voltage regulator does is it measures the terminal voltage and current, and based on a feedback loop, provides the signals to the excitation system to provide and the turning on of the rectification system to provide the required DC current to be fed to the rotor winding to set up the required magnetic field to produce the required reactive power that will basically regulate the terminal voltage. If for whatever reason, let's say this excitation system, like I indicated, that what it does is it has a dedicated, let's say for a static excitation system, you have a dedicated transformer, right, that has an AC voltage that steps the voltage down to a lower DC voltage that is fed to this exciter that converts the AC voltage to a DC voltage equivalent. For whatever reason, if you lose, you should lose this transformer, right? That means that your excitation system is going to be out. If for whatever reason you should lose this is your voltage regulator controls. If you should lose your excitation system, right? That means that your excitation system is going to be out. So that is when your loss of excitation system comes into play. So based on a relationship between your magnetic field and your impedance, the magnetic field that sets up on the rotor, that revolving magnetic field, basically equates to an impedance locus, right? Okay, so let's say if your magnetic field during steady state without any problem, it corresponds to a certain ohmic impedance. But for whatever reason, if you should lose the magnetic field, then basically your impedance drops and basically falls into this ohmic circle. Then that is when this protective relay element detects a fault due to loss of excitation and trips the generator. Next is inadvertent energization, right? Okay, so this is a 50/27 element. The 50 means instantaneous overcurrent, and 27 is under voltage element. Okay, so you have a turbine generator set, right? That is integrated to a step-up transformer. Then you have a breaker before it goes to the grid, right? Okay, so this comes to the terminal. You have 18 kV. That is step up to, let's say, 115 kV. Then you have a breaker here. When you take off this turbine generator set, right, offline, right, okay, through basically tripping off this breaker. So if this breaker is open, right, okay, then the turbine generator shaft will be on a turning grid, right, because it is hot, right. It has an embedded heat, and that embedded heat takes time because of the time constant, for the heat to dissipate. Aside to prevent bowing of the turbine generator rotor shaft, basically it is put on a turning gear. So there's a turning gear motor that basically constantly rotates this turbine rotor shaft to prevent bowing of, and which basically can result in vibration problem. Let's say for whatever reason, due to operator inadvertent error, if an operator should close this breaker, right? What happens? Then basically this turbine generator is going to operate as an induction generator and basically start in an induction motor and start drawing power from the network, right? So what this protection scheme does is basically it's going to protect the generator from inadvertent turning on of the breaker that can cause the turbine generator to act as a motor. Next is a loss of prime mover, right? Okay, so you have a turbine, right? And within the turbine, basically you have different sections. You have the high pressure sections. You have the intermediate pressure sections. You have the low pressure section, right? Okay. So let's consider a steam turbine generator, right? Okay. So you have a boiler here, right? That basically, has basically you boiling, let's say, a coal, pulverized coal, right? And has basically water flowing through the walls that it converts it to steam, right? Then from there, basically piping steam flow through a piping that comes into the high pressure section, right, and hits the turbine blade. So that's how the shaft of the turbine start turning to convert into a mechanical power, right? Okay. Then it comes to the bottom of the high pressure section of the turbine, and basically it goes back and gets reheated to make it more dry, right? It goes through the boiler and through the top section. There's a reheated core here, gets reheated. Then it comes back into the intermediate section of the turbine and hits the turbine blades, right? Then from there, it's a crossover, right? Then it comes into the low pressure section, hits the turbine blade. Whilst this turbine section, is still, continuing to basically rotate, right? Then basically it goes into a condenser, right? It comes into a condenser. Then basically the steam collapses, right? Because the turbine walls has cold water. So once the steam hits the cold water, basically it turns into a condensate. And there's a condensate pump motor that pumps the water. Then it goes through the feed water system and also boiler feed pump. Then basically it goes back to the boiler. And the cycle basically is a closed loop. Cycle repeats itself, right? Okay. So for whatever reason, if you should lose this steam due to a boiler trip, right? Then basically, once the turbine generator is integrated to the network, the grid, right, it's going to act as a motor and start receiving reverse power. Instead of pushing power in the forward direction, it's going to receive power in the reverse section. So what this protection element does is it protects the turbine generator from a reverse power. Next is out-of-step condition. Okay, so for out-of-step condition, you have many generators, right? Let's say about 10 of them that are all tied, operating in synchronism. All of them have a transmission network, right? That are all tied together, right? So that's how you achieve that vast transmission network. So if for whatever reason now, if one of them should lose synchronism, right, that needs to be detected and for this generator to be isolated as quickly as possible, because other than that, this is going to cascade to the other generators and they will all lose synchronicity. Next is overload condition. Okay, so overload condition comes into play when you have a generator that picks up a load, right? So you have the overload curve, and the set point is, let's say, 1.25 times the full load, right? So once it exceeds the loading exceeds this set point, then that is when this relay basically picks up and starts timing. Next is blown fuse, right? Okay, so for the blown fuse at the terminal of the generator, right, you have a PT. Okay, so for the PT, let's say if the generator terminal voltage, right, is 18 kV, then the secondary voltage is let's say 69 volts line to ground, or 105 volts line to line, right? Okay, so this is what is fed. This is the voltage that is fed to the metering devices or protective relay elements or the extension system, the voltage regulator. That's what goes into the voltage regulator to act as a feedback loop. So if on the high side is a fuse, right, in each phase, then on the secondary side are fuses, right? If for whatever reason you should have an open circuit on one of the phase due to a blown fuse, right, that is when this relay element is going to detect that and block tripping of the generator, because it is a blown fuse, right? It is not a fault, which will cause the voltage to decrease. So that basically blocks tripping of the generator based on the blown fuse. Next is thermal protection, right? Okay, so inside the winding, the center winding of the generator, right, we have RTDs, resistance temperature detectors, that are embedded in the slots of the winding, right? Okay, let's say you have a top coil, the bottom coil, right? In between the top coil and the bottom coil, in each slot of the coil, right, that is where the RTDs are embedded. And normally you have about 2 or 3 RTDs that are installed per phase, or sometimes you can even have all the way up to 6. That redundancy is put into it. So what this does is this RTD element is it measures the resistance due to the heating of the embedded heating, the build-up of heat in the winding. Right? So if for whatever reason there should be a short circuit, right, basically it's going to cause a heating, right, and change in resistance, and that can result in heat buildup. And so that's how this protection element protects the generator. Okay, so in the previous slide, right, we talked about all the abnormal conditions that basically requires that protection for the generator. Now let's talk about the electrical protection, right? Okay, so the main protection for the generator is differential protection, right? Okay, so you have a generator, right? We have in, out, right? We have a CT here, right, that is tied to a differential relay, 87 G, right? Okay, so inside of the 87 G relay, we have a restraint element, right, on both sides. Then we have the operate element based on the difference in current from here. That is when the operate current flows, right? Here is the restraint. Okay, so basically what this differential protection element is doing is measuring the current input into the generator and what is coming out of the generator to basically make a decision based on a set point of minimum operating point. The minimum operating point is selected based on a lot of factors, right? And that is basically put into place. That is based on basically, you know, CT characteristics, right? Where a percentage is basically factored into that to decide on the minimum operating point of the differential relay. Next is our steady overcurrent, right? And this is a 50-51 element. The differential is 87 G element, and the steady overcurrent is a 50-51. Okay, so that basically protects the generator due to an internal fault on the phase, right? That is a phase protection. Next is a loss of excitation, and I think I did basically discuss that. Next is a negative sequence protection, right? Okay, so for whatever reason, during an outage, if you should have a phase reversal, right? Okay, or let's say during normal operating of let's say you should have an unbalanced voltage, right? In each phase A, phase B, and phase C, right? Okay. What this protection element does is it protects the generator based on an unbalanced difference in voltage between each phases, right? Okay, so for each 1% unbalanced voltage, it translates into 6% negative sequence current. So what this protection element works is based on the negative sequence current squared times a time duration, allowable time duration that the manufacturer will provide to you. Manufacturer will provide you a chart that you will use based on time, negative sequence current, allowable for you to do your settings, and the maximum negative sequence current that the generator, based on the different types of generators that we have, that it can withstand. So that's what the protected relay engineer uses to set. Next is a reverse power, and I think we did talk about in the previous slide. Next is out of state, right? Okay. Next is 51V. Okay, so this one is a backup protection to the differential protection, right, for external fault, right? Okay, so if you should have an external fault, right, all the way inside the grid, right? Okay, and if all the protection elements fail, right, what is going to happen? Okay, because this fault is so far off, right? Okay, the terminal voltage will be very, will dip slightly below the nominal terminal voltage, and sometimes even the current that is going to be sensed by the differential or overcurrent protection will be very small, quite close to the nominal currents, right? As such, what this 51V voltage control overcurrent element does is it measures, basically it tracks the decrement of voltage with current, and that's when it picks up. So it's a backup protection for the generator due to an external fault where the external protection relays fails to clear the fault, and basically you have the fault basically intruding and basically evolving into the generator. Next protection is volts per hertz over fluxing, right? Okay, so what this protection element does is it protects the generator from overfluxing condition. And when do we get an overfluxing condition? Due to load rejection, right? Okay, let's say if the generator should reject a load, then basically you should have over voltage condition that basically can result in the saturation of the core and can result in an overfluxing condition. Okay, so what this protection does is it's basically provides protection for both the generator and the generator step-up transformer, right? So from overexcitation condition. Okay, so next protection element, it's steady ground, right? Okay, so this basically it's a high impedance grounding scheme, right? Where basically you have a single phase distribution transformer, right? That is basically utilized to be used as a high impedance element reactor, basically to limit the ground fault to up to let's say 10 amps to 25 amps, right? Okay, so on the secondary side, it's a resistor that is connected across the secondary winding. Then across the resistor is this 59G element, or one thing is the 59G element or the 59N element. That is, it provides a 95 protection, 95 state of ground fault protection. So the remaining 5% of the neutral of the generator is unprotected, right? So you need additional protection to cover the 5% or basically overlap it to complement the 95% protection. So that is when we utilize the undervoltage third harmonic protection, right? Based on the philosophy that each generator has an embedded core that basically generates a third harmonic. That is very natural to each generator. Each generator has a unique signature of third harmonic current, right? Okay, so this during operation of the generator, this third harmonic voltages basically manifests itself. So during state of ground fault, right, there's a reduction in this third harmonic voltage that is manifests itself during steady state, right? So the reduction of that basically is what is used by this relay to complement the 59G or the 59N to provide a complete 100% state of ground fault protection. Next is another state of ground fault protection that can be used, but this time this one basically provides 100%, right? Instead of utilizing the 95% 50G, 59G, and 5% 10 harmonic under voltage, you can go ahead and utilize a complete 100% setup. What this does is it utilizes a harmonic current injection at let's say 20 hertz, right? That is injected from the neutral of the generator inside the, so this one is basically connected, online. Basically, it's a real-time measurement, right? Okay, so during ground fault, basically this injected harmonic current basically will give back a voltage, and based on the impedance that is measured, basically it will detect a ground fault. Next is a backup state of ground fault, right? Okay, so this one is a backup for all these different state of ground over voltage faults that we have. If they should fail, then this backup fault protection should be basically should take place. So basically this is installed on the side. This 51G, right, installed on the side. Next is a rotor ground fault, right? Okay, so basically there are different schemes, right? Okay, there are schemes basically that utilizes current injection schemes to detect a shorted winding on the generator rotor. Next is a generator main step-up transformer overall differential, right? Okay, so you can have that overall differential scheme depending on the criticality of the generator, right? Let's say if you have a generator that basically is provides power and to critical customers, right? Then basically there's an additional barrier that is basically implemented, to provide an overall differential scheme, right? Okay, so you should have a 87G that basically provides a differential scheme for the generator, right? Then you should have an 87T that provides a differential scheme for the power transformer, right? So this 87 overall basically provides a overall protection scheme for both the generator and the step-up transformer. So that's how this protection element does. Next is under and over voltage protection, right? And this is designated by 27 element for the under voltage and 59 element for the over voltage. That is you can have an under voltage condition when the generator picks up excessive load, right? Then the voltage goes down, the terminal voltage goes down. Then you can have an over voltage condition when the generator rejects load. Especially, it comes into play during a load shedding scheme, right? Let's say, if it becomes necessary for load shedding to be implemented, then that is when over voltage condition comes into play. Right. Next is under and over voltage protection, and I did talk about that in the previous slide. Next question, typical question on power transformers protection. It's tell me about the different power transformer protection schemes that you know. Okay, so this is how you. Okay, there are two types of protection schemes for power transformers: the electrical protection and the mechanical protection. So now let's talk about the electrical protection piece, right? Okay, so for the electrical protection, this is basically incorporated for power transformers that are critical, right? That is feeding critical customers, and also for power transformers that are 5 MVA and above. Okay, so the first, it's a main differential protection, right? Okay, and like I explained for the generator differential protection, same philosophy, right? You have a transformer, right? You have a in, out, right? You have a CT here, you have a CT here, right? That is basically connected to a differential relay element, right? That measures, basically takes a differential of based on a set point to basically activate this. Then you have a backup protection, right? The backup protection usually is on the high side, right? Okay, so you have a 50, 51, right? Okay, this is instantaneous and time over current, right? If for whatever reason, if your differential protection should fail, right, then your fault is going to evolve, right, into, so there's a high set point, let's say 10 to 12 times your full load current. That is when this instantaneous element that comes into play. Then your time over current is based on overload, right? 1.25, then basically it picks up and starts time. Then another protection scheme is magnetic inrush, right? Okay, so during energization of the transformer, the differential relay should be able to distinguish between a true fault and a magnetic an inrush condition, right? The inrush condition is rich of harmonics, even and odd harmonics, right? So we utilize the second and the fourth harmonics as a blocking inhibitor to prevent the tripping of the differential relay for the for the transformer to ride through energization. Then during energization, there's the possibility of overextension connection because there's no load connected to the load side, the secondary side of the transformer, right? Okay, so there's the possibility that an overextension condition should okay. So we utilize the third and the fifth harmonic content of the inrush current to identify an overextension condition during energization to prevent block the differential relay from tripping. Next is a restricted egg fault, right? Okay, so the main differential protection for the power transformer is the main protection scheme is the differential relay, right? Okay, but if you have a delta Y transformer, right, that is grounded, it could be resistance grounded or solidly grounded, right? Okay, and then usually it is applied to solidly grounded relay. Okay, so or there's a possibility that you can also apply it to resistance grounded. Okay, so at the neutral of the transformer, right, the differential protection cannot cover protection at the 5 to 10% area of the neutral, right? Okay, so when there's a ground fault here, right, there won't be enough differential current to be able to drive a fault voltage for the differential relay to detect a fault in the last 5 to 10% of region of the neutral of the Y wound transformer. As such, we need a sensitive protection element. So that is how the restricted air fault protection is utilized. It's a high sensitive protection element that is utilized to complement the main differential element of protection to basically it is applied in an overlapping condition to be able to detect ground faults in this area of the Y band. Okay, so but there are two types. We have the high impedance, right? The high impedance basically utilizes it's called 87N, where basically it is utilizing the residual of the phase and the neutral CT. It is utilizing that, compares that. It is utilizing the residual of the CT measured phase current and the neutral current to basically compare and identify if there is a ground fault. Right. Then the low impedance basically it's a restricted air fault that is basically applies in this region. Next is a surge arrestor protection, right? Okay, so surge arresters are mounted or quite close to the bushing terminals in close proximity to basically provide protection, lightning protection, switching surges protection for the power transformer due to an overvoltage condition that can result and basically can destroy the transformer based on that. Okay. And for generator step-up transformer, I remember I made mention, where basically we can utilize the volts per hertz protection element to provide overextension condition. And this is a combination of the generator and the step-up transformer combo. So now let's talk about the mechanical protection, right? In the previous slide, we did talk about the electrical protection elements for the transformers. Now let's talk about the mechanical protection element. The first one is sudden pressure device, right? So the sudden pressure, if let's say you have a main tank of a transformer filled with oil, right? The sudden pressure device is mounted on the sides, right? And depending on the criticality or the application of the transformer, you can have more than one sudden pressure relay, because the sudden pressure relay device, it's a mechanical device, and basically it is prone to spurious tripping and spurious alarming. So in the nuclear environment, two sudden pressure relays are utilized, one mounted in each corner, where both sudden pressure relays have to experience the fall, right? The pressure wave from the oil. Before basically they will all basically identify that, okay, indeed we have we have a fault condition. So basically provide an output for the to trip the breaker. Okay, so this is how this protection element works, right? Okay, so if you should have a closing fault, right, or you should have a through fault, right? A through fault means that it goes through from basically the source, right? It goes through the transformer from the high voltage side through the transformer to the low voltage side, right? So that has to be a fault on the low voltage side. So that's how a true fault works, right? Okay, so if a true fault should go through the transformer, because the transformer is filled with oil, right? And the short circuit current, because it is so high, it translates into high magnitude of electrodynamic forces, right? And these forces basically creates a pressure wave that creates a wave that basically impinges on the bellows of this sudden pressure device. And basically it is wired to inside that has a micro switch that is wired to an auxiliary relay 63X. Then it goes to a lockout relay before it goes through the trip coil of the circuit breaker. Next is our pressure relief device. Okay, so the pressure relief device is mounted on top of the transformer, right? Okay, so that is the last resort of protection. If all the protection elements should fail on the transformer, right? Okay, so if the sudden pressure relief device protection should fail, if the differential should fail, if the backup 5051 element should fail, then by the time the fault would have evolved into a big pressure inside, because this one becomes basically a pressure vessel, right? Okay, so that pressure has to be expunged. So that is when this protection element detects the build-up pressure and basically opens up and expunges all the oil to the outside world. Okay. Usually, this relief device is used for alarm purposes. Next is the oil temperature gauge, right? Okay, so inside the transformer has oil, right? Okay, so there should be a way of monitoring and protecting the transformer utilizing an oil level gauge, right? So this one is a 26Q element, right? So based on the level indication, right, you'll see that, okay, we have the high, the low, and 25 degrees. This is the indication that is shown on the oil level indicator. And let me explain to you why you see the 25 degrees Celsius. Okay, because the oil is filled in the factory at a room temperature of 25 degrees, right? Okay, so let's say if this is the oil level, right? Okay, so between the oil level, the top oil, and the top metal that is right here, right? The top cover, right here. There is a gap, right? And that gap could be, filled with, let's say, a nitrogen blanket. right, to act as a cushion, right? Okay. So if this transformer, let's say in operation, basically the oil expands and contracts based on the elements, based on the outside temperature, right? Okay. So if the oil level should expand, right, then this indicator is going to go up, right here. If it should drop, then you see that it's going to come down, right? So it's been calibrated, right, that based on the changes from the top of the oil to wherever it is, right, there's an inches, right, based on, let's say, 1 degree rise or fall in temperature. So that's how the calibration is done for this oil temperature gauge. Okay, so next is winding temperature, right? Okay, so as you know, current is flowing through the coil, right? The coil is copper, right? And current flowing through it basically creates heat, right? So there has to be a winding temperature gauge that measures the hotspot temperature, right? And that basically the indication is shown on a gauge that is mounted on the side of a transformer. Next is top oil temperature. Top oil temperature, right, is right here. And basically it is measuring the top oil that basically you have, and basically this is wired to all the stage cooling fans that you have, right? Okay. Next is the Buchholz relay. The Buchholz relay, it's another device for 63 X. That is basically for conservative tank, right? Okay, or free breathing transformers, right? So if you have a free breathing transformer, you have a conservative tank, right? If it is a tank, then you have a piping, downcomer piping, then you have the Buchholz device, and basically that protects the transformer based on low oil level, incipient fall from gassing, right, and through fall, right? If you have a through fall condition, the pressure wave of oil is going to flow backwards, right? If you have an incipient gassing, basically the gassing is going to create as a result of broken connections, short returns. Basically the gassing rises and collects into a chamber. Then based on the volume, basically it activates an auxiliary relay. Then basically it goes to lockout relay, then trips the transformer. Then for power transformers, let's say distribution type power transformers that are 5 MVA and below, usually they utilize a fuse protection and overcurrent protection. Now let's talk about motor protection, right? Okay, tell me about the different motor protection schemes or elements that you know. Okay, so for motors, right? Okay, you can say that, okay, for motors that are larger than 5,000 horsepower, usually we apply differential protection, right? Okay, so the differential protection for motors is quite similar to the differential protection for generators and transformers, and basically I've explained it in the previous slide, right? Okay, so motors in general, right, let's say 1,000 horsepower and below, they are connected to 600 volts, and greater than 1,000 horsepower and above, it's 4.16 kilovolts, right? And they operate at 4,000 volts. Okay, so next is instantaneous overcurrent, right? Then time overcurrent. So a time overcurrent, right? If you have time, then multiples of pickup of current, right? Okay. Okay. Now let's take a look at this is the time damage curve, right? Of the motor, right? Okay. And this is the acceleration curve. Okay. So if you start a motor, right? Okay. So here it's, let's say, 6 times the normal full load amps, right? Okay. So this is when, beyond that is when the lock rotor comes into play, right? Okay. So you start a motor, basically, the motor starts accelerating, right? Then, so this is the acceleration section of the generator, right? Okay. Then when it gets here, basically it has accelerated to full load speed, right? And full load current. So the full load current is right here. So if this is the thermal damage curve of the motor, right, there are various sections. So this section is the acceleration region. This section is the lock rotor region, right? And this area is the thermal overload section, right? Okay, so you set the time over current element to coordinate. It should be in between the thermal damage curve and your acceleration, right? So that is why when you're setting the time over current, it should coordinate with your thermal curve right here, then your lock rotor and your starting current. So that's how the coordination should take place, right? Then overload protection, right? So within this overload section, this is where basically the coordination with the thermal capability curve of the motor takes place. Next, under voltage, right? Okay, so if you have a motor that is connected to a bus, right? Okay, A, B, C, right? Okay, you have a PT, right? That basically, let's say if you have a 6.9 kV bus to, let's say, 115 volts, right? Okay, so if you should have an under voltage condition, right, due to fault, right? Okay, basically the voltage is going to go down, right? Okay, so that's how this under voltage condition occurs. Okay, then over voltage condition, right? Okay, so over voltage, similarly, you know, if you have an over voltage condition due to whatever condition, then this is the protection element that basically protects the motor. Next is negative sequence, okay, phase unbalance. Let's say if you should have an unbalance in voltage between phase A, phase B, phase C, right? This is basically the protection element. That is ANSI device 46, right? And like I indicated, for 1% phase unbalance voltage translates to 6% negative sequence current. Next is negative sequence voltage, and that is based on phase reversal. Let's say if a motor is taken offline and let's say maintenance is performed, and let's say for whatever reason there's a phase reversal of wiring, it could be from the VTs, right? And wiring, then that is when this protection element comes into play. Next is lock rotor, right? Okay, so during starting of the motor, right? If the rotor of the motor locks in place, right, and fails to turn, and there are many, you know, let's say low voltage condition, right, non-adequate voltage that is needed for the motor to accelerate to attain the full speed, right? That could cause a lock rotor condition. Let's say high loading condition, the coupled load is so high that is going to cause the motor to lock in place. So that is when this protection comes into play. You can also have a mechanical jump in place, right? Let's say during the operation of the motor, right? Okay, you can have let's say all of a sudden the voltage basically, you know, there's a fault and the motor basically the voltage decreases, right? Then basically the motor is going to jump. So this is what basically the protection element that protects the motor. Next is a winding temperature. Okay, so similarly to the generator, right? Okay, we have RTDs that are embedded in the slots of the core, right, in between the windings. That basically is able to produce resistance measurements that is translated into temperature measurements to be able to detect the inside temperature. Because you know, as the motor is operating, there's build-up heat, right? Anytime you turn on and off of the motor, you build up heat, right? Okay, so that is why there are other protection schemes that is utilized, you know, by motors based on the thermal model, right? To basically mimic the building of heat to basically that is iterated to the number of allowable starts, you know, and stops of the motor. Next is a bearing temperature protection, right? Okay, so you have a bearing, right? Okay, that is basically, you know, you have the shaft, right? You have bearings, right? Okay, definitely we have RTDs, right? That are basically embedded in the slots of the bearing. Let's say you have a sleeve type bearing, and a sleeve type bearing, you have a Babbitt material, right? You have this embedded RTDs that measures, you know, the temperature, you know, based on so the goal is to basically to prevent the damage of the bearing due to excessive heat, and also the barbette material, excessive wear of the barbette material inside the bearing. Next is vibration, right? Okay, very important. When a motor is especially critical or larger horsepower motors, basically vibration monitoring is incorporated basically based on the speed of the motor. Different accelerometers are utilized to basically measure the vibration. Next is for all the protection elements that I've explained above basically are applicable to induction motors and synchronous motors, right? But synchronous motors have additional protection elements, and that is what I'm going to talk about. Okay, so as you know, synchronous motors basically utilize is an extension system, right? You have the rotor, right? Then you have the stator, right? Okay, so an extension system, just like the synchronous generators, right? Extension system is applied to the rotor, right, to provide the revolving magnetic field, right? Basically, that is going to sync up with the revolving magnetic field of the stator for it to rotate in synchronism, right? Okay, so protection system is needed for the extension system and basically loss of extension system. And you could also have an overextension system, right? Due to excessive current. Like I said, due to different malfunction of the extension system, you can have excessive current, DC voltage and DC current flowing into the rotor winding that can cause heating of the rotor winding. And there's a measurement that is indicated by this relay to detect that condition. Then you can also have a power factor protection, right? Okay, and based on the power factor VAR measurements that is measured on the terminals of the motor. Next is a typical question. What are the information and parameters needed for motor protection? As a protection relay engineer, as a discipline relay engineer, you should have a basic knowledge about, even if you don't do the settings, right? As a relay technician, as a maintenance technician, electrical technician, as an operator, at least have a knowledge of what are the input informations that a protection relay needs to perform the settings of motor. Okay, so the first one is the full load amps, right? Okay, so the full load amps will be seen on the nameplate of the motor, right? And the manufacturer will also give you the technical data sheets for the motor, and you see that parameter to provide it to. Then the horsepower rating, and that's very important. Then the service factor. The service factor basically comes into play for overload conditions. So you can have a service factor of 1.15, 1.25. That itself tells you how much overload that the load that is coupled to the motor you can have, right, above your nominal rating. Then your lock rotor kVA per horsepower, right? This basically allows you to do your setting for your instantaneous settings, your 50 settings, right? Okay, so that should be multiples of your lock rotor, right? Okay, so let's say 6 times the lock rotor amps, right? Okay, and now your lock rotor kVA per horsepower, you can get it from basically there's a code, a letter code, A, B, C, D, E, F, E, right? That is from the NEC table, right? That tells you based on the lock rotor code that you see on the nameplate or your technical documentation that your manufacturer provides to you, you can utilize the NEC table to check the amount of kVA per horsepower. Then the acceleration time, right? Okay, and I told you that, okay, you have acceleration time, right? Basically, that allows that protection relay engineer to basically to coordinate the setting of the acceleration of the motor with the thermal limits. Then the voltage, then the frequency, then the thermal capability curve, basically that provides the heating and the cooling constant. So basically, you can have if this is the lock rotor region, right? You can have the hot, the cold, and the hot time. Right. Then acceleration, you can have the hot and the cold. Right. Okay. So that's how you get all these times and basically to obtain the time constant as well. Right. Okay. Then your acceleration time. That's what I told you. You start a motor right here. then you accelerate, lock rotor conditions, then accelerate, then you achieve full load. This is the acceleration time. Then the starting curve, yes, this is what you need, because you need that in the thermal damage curve and the thermal limit curve to do all your settings over here, your 50, 51 settings, and your thermal overload settings has to coordinate with this thermal limit. Then allowable temperature rise. Yeah, very, very important, right? Okay, because that basically gives you the margin for you to set it with the thermal limiter curve. With that, it comes to the end of my presentation, and thank you so much for your listening ears. And look out for your the next presentation as part of my presentation series. Right? And I would like you to visit my YouTube channel, and that is shown over here, right? Okay, that is shown over here. Just go there. There are tons of presentations, tons of information, tons of knowledge that you need. Then, if you like my presentation, don't forget to select the select button, in YouTube. Don't forget. Then share. Then subscribe to my channel. Okay. With that, thank you so much, and thank you also for your listening ears. Thank you.